Hello. Morning, good afternoon, and welcome to this webcast. Time to start. Quickly check if any other hiccups. Looks like all okay. Let's start. Before I start, I would curious to know on some of you had a chance to on my last two webcasts. Did you my training yesterday on sticks? Feedback through the chat window? It is just curiosity. If anybody attended simulation and are coming here today for flow simulation? Excellent. If you are here for the first time, okay, if you who attended simulation also, excellent. So thank you much. Let's start this session. It is going to be long, 90 minutes. So to cover and an interesting topic in the CFD field, simulation of flow. Let's go ahead with it. I'm Kapil Gaitonde. I'm the Territory Technical Manager for SolidWorks Simulation and based Singapore. I'm covering Asia Pacific South countries and India for this simulation product. So first of all, what are we going to see today, or what are we going to cover today? It would include of product introduction. I want to ensure that you all are aware on the capabilities of the software. So let's have a look at the different capabilities and what it can do. Let's have a look at what would be the basic minimum things that are required for simulating a fluid in SolidWorks flow simulation. In examples, I'm taking up three interesting examples. The first is a simple one, which is of a wall. See how we simulate flow inside the wall. There's a conjugate heat transfer. This is a theoretical word, but really what it means is moving from a solid component to a fluid. So in the heat change happening between two fluids, between liquid and fluid, and the example that I'm using is of a heat exchanger. So you'll have a look of how we simulate multiple fluids and heat exchange between them, find out the efficiency of heat exchange, etc. And we will example on rotating components. The example that I am using is of an impair. We'll simulate it in our software, how to create the setup and how it works. So on a quick note, I'll wind up with two examples. One of them will be on HVAC, that is heating, ventilation and air conditioning. And the last one will be ECS, that is on electronic cooling system. We'll see an example on a enclosure. Let's see how it is being simulated. HVAC will have a look at if a pollutant is created in a certain environment, how the software will help you to simulate that. As this is the beginning, I'll just have a quick look. Any inputs on? Yeah, excellent. Everything good. Let's move on. We have simulation and plastic. The last is today we are moving on to flow simulation. So in flow simulation, if I sum up, these are different capabilities that it has, and you start with the basic, that is flow simulation basic capabilities. The foremost is what we call as internal and external flow analysis. So of a wall, this is the one that we'll be simulating today. Let's have a look on how we do it, what are the steps, what flow simulation needs to simulate this particular wall. So also with this, you'll be able to simulate a wall as an internal flow analysis, as we need closed volume to simulate such a scenario, and it will be one of the basic minimum requirements for doing this setup. But could also be cases wherein the fluid is flowing in internal case, the one as shown on the screen. You had a pickup. Now it should be okay. Yeah. This is an external flow analysis. This is an aeroplane is flowing around it, and we are simulating the forces coming because of the system. So, the example of an aeroplane, but it could be other components like wind turbines, vehicles, two-wheelers, four-wheelers. It could be huge buildings, cranes, or the external signs. You want to understand the forces coming because of external flow. So this could be the second case. We'll see how we go about it. Where are the options? So this is the basic part of it where we understand the pressure and velocity distribution in a fluid domain. We understand what is the kind of forces that this particular fluid is going to exert on the system. Heat transfer. I told you this. The example is shown on the screen is of that electronic enclosure. Similar example. Here, the heat created by different electronic components. The fan which is blowing the air through the system and throwing that air outside. We can understand, or we would like to understand how many fans to have, where to have them, where is inlet depth, such the temperatures are maintained at a certain level. So this example of a heat exchanger, heat transfer. Covering an example on heat exchanger, we'll look at it when we go into the software. Next components, there could be many, but the one that is shown on the screen will be what we'll be simulating today. If a pump, rotating impeller pump, will how fluid, how pump simulated or such rotating components are simulated in our software. Some like it is not only the simulation of fluid, but you have capabilities which you can transfer this fluid load to shell load and do structural analysis on the components. Not only the fluid flow, but move them to structural and do the stress analysis. So this transfer can be to our simulation software, and it is not only forces and pressures that are coming on the structure, but also be the heat transfer happening because of coefficient of convection. So we understand that aspect as well. A few more minor things. It is both compressible and non-compressible fluids. Compressible examples could gases, most are compressible. Liquids like water, oil, etc. could be the examples of non-compressible fluids. Is a Newtonian flow or a non-Newtonian flow? This is more based on the speed of the flow. Islands that comes into the picture. It's cool or turbulent, so both can be simulated in this software. Finally, time dependent. So it's scenarios wherein the flow will never become steady. It will be continually oscillating, and we understand a phenomenon will be seen over a period of time. So if the animation that is shown on screen, there is a continuous movement, especially if you see the gray area over there, continuous oscillation of fluid. So what would be the basic capabilities of flow simulation? This is a big. And to add to that, we have two other specialized modules. One is called as electronic cooling, and one is heating, ventilation, and air conditioning. Electronic cooling, we can, first of all, if you observe in both these things, getting an extended database. There is a huge database that will get added in these two modules. Electronic cooling system has a database which is oriented towards electronic components. It could be like a huge set of fans, things, heated circuit boards, or the chips which are represented as two resistor components. So all those things are present in this particular database. In the if it is heating, ventilation, and air conditioning, then more towards the requirements of building materials, like fans will be there. Apart from there, it could be like concrete, it could be wood, it could be the walls that are present which are necessary for simulating environment, or extra material will get added in this database. Capability, if you see over there in electronic cooling, one of the basic and interesting part would be we'll be able to simulate the amount of heat that is created when through a conducting component. So that's what is called a Joule heating. Apart that, we can simulate the enclosure. Need not model or create electronic components like heat pipes, PCBs, uh, fans, etc. And this can be automatically taken from the database and used in the software. So these are over here. Followed a few other things like, okay, moving on to HVAC, that is heating, ventilation, and air conditioning. Or the most important output or the parameter that would be of interest to user will comfort parameters. A huge set of parameters which will help us understand if a certain person within this environment is comfortable or not, and based on a few parameters like predicted mean vote, predicted person dissatisfied, etc. Really, a human being will be comfortable in a certain location if certain quantity of oxygen, if a certain quantity of air around him with a certain speed, temperature should be of a certain level. These parameters together decide if a certain if he is comfortable at location or need to improve the system. Moving on a tracer study using which we'll have an example on this one. Usually can understand if at all there is a pollutant inside the system. It is more of a kitchen and we are showing carbon monoxide being created at a certain location. I think all the carbon monoxide will spread out in this system. So showing us if at all there is a pollutant, how is the pollutant dispersed in the system and which uh, in the closed or the open environment. So this interesting feature is available in over here. And the radiation effects. And HVAC has capabilities to understand the radiation effects that can happen within a solid component. Whenever light or radiation moves to a transparent component, it creates certain amount of heat inside it and have an understanding of what is the level of that particular radiation. Like to say these are the basic categories of flow simulation. Before ahead, I would like to take a quick break to 3 minutes, check if there are any questions, and after move ahead with it. Any questions? Question. This says that we that fluent results to be imported into simulation module, but we import flow simulation into motion module. Example would be an electric motor with a propeller. Identify the torque and used to spin propeller at a desired CFM rate. Frankly, I would put it other way around. We need not pick the flow simulation results into all the way to motion to do this thing. In flow itself, we have capabilities by we can find out the torque coming at a certain location. So turbine or a fan and it is subjected to certain amount of wind load. We can understand the amount of momentum or torque that would come at the axis of that particular component. And I believe that should help us understand necessary torque required to resist or create that kind of momentum in the system. In terms of taking the load all the way from flow to motion, I think it would be similar because ultimately we are taking to simulation. We also that we can take loads from simulation to motion. So if necessary, even that can be done. But as that is not required, you can directly do it in flow simulation. So for the capabilities, please use the chat window instead of the question panel. That will be easier for me. on the topic that I covered as of now? See any momentum? So let's move on to the actual software, how it works. Okay. First of all, let's have a look at what are the basic minimum things that are required for simulating a particular fluid. To start with, we saw something as internal flow analysis. So over here you saw that we need to have a closed volume. Okay. So given any setup, if we want to do that, we need to create in SolidWorks, or we have very good options in flow station itself by which we can create such a closed volume. So that's first requirement. That we need to understand the fluid that is present, whether it is a liquid, gas, whether it's Newtonian fluid, non-Newtonian, what are the kind of speed coming in this, whether it will be a turbine will be involved, or whether it is going to be a steady state flow. All those, at least a basic idea on the fluid is necessary, and we can either use the software list of used material database of fluids or liquid, and if necessary, we can also create our own system. Setting conditions, that is the pressure, velocity, temperature, etc., in which this particular system to work. So that will help us understand how to create in this software. Especially those who attended my simulation training, please note, unlike what you saw in simulation, in simulation, realistic boundary conditions are very important. A bit of variation from the realistic boundary conditions will create incorrect results, or the expectations can be very wrong. I would just to always ensure that we are at least, if not very accurate, close to the realistic boundary conditions. We not try any particular input or any particular output over here. The output should be realistic and it makes sense. Fine. Now, this is a bit of differentiating in flow simulation, wherein there are number of outputs that can expect from a software, and especially CFD software. So we need to know which output is very important to us. The which is more on a convergence criteria based solution. So obviously, if we tell this software on which are important parameters which are relevant for us, then do the iterations on those parameters and ensure they are converged. So you can, to take an example, if for me the interesting, most important part is the torque that is at a certain location in this setup. The example that I answered that gave a few minutes back. Then we ensure that the torque is converged, and we can also give the tolerance. We want to ensure that the torque is converged to a level of plus or minus 1 Newton. So we need to specify. On doing that, the solution will be converged. If we don't give any goals, the software will not converge. It will do it on its own. For accuracy, it is always good that we know what we want and ensure that that particular result is converged. Coming to once you have the software and you have taken the evaluation license, the examples that I'll be showing you today are at this particular location, which is held solution for flow simulation online tutorials. So this location where all the tutorials are present for flow simulation. What I'm doing today are these things. Under this particular PDF, you will see something called as first step. I will show you where exactly it comes. And example on ball wall design. Second would be on a heat exchanger. Third one would be a rotating component like an impeller. And we'll see two examples. One is on HVAC and electronic cooling system. So to the software, so we find this example. As I told you, once you go to Help, SolidWorks simulation, you'll see something called as flow simulation online tutorial. So here you'll find different examples. The one that I'm covering over here is this one, ball wall design. an example on heat exchanger, and finally an advanced example on SL. At GCS, I'll be covering an example on constant dispersion and electronic component. So here, highlight once you get the evaluation, you should be able to see a thing called as technical reference. I suggest given answer, please go through this. This is exhaustive manual, very good theoretical inputs on the different deals of the software or any C of the software, the way it works, etc. It also has a few more validation examples which you might want to try. More of textbook examples which you can try in the software and have a look on how they work. I would suggest, apart from the tutorial examples, try to do those examples as well. Now on to this example. It is on a wall. Just show you the setup the way it is. Before, I would like to create a configuration which I'll use now for analysis. I believe we're on how to create a configuration and what is the relevance of configuration. I can say there is one question which says that can we get the model of the ball wall? So actually, once you have the software installed and the location, I believe I have given, no, I have not written it. I'll add that text over here. The file set is present under installation location, program files, flows and examples. So this particular location, you should to see all the examples. The first one is of that of the ball wall. So it's a ready-made setup as well as one that has been created. You can which one to use. I will add text in the presentation and I will share it with you as well. One. So example, if you see over here, it includes different first of all wall components, two standard components which are necessary. The wall, and it includes the ball, a handle, and two sides. Two which are created as per the requirement of are these two lids. Now, either we can create those lids in software. If you see over, go to simulation to create. For simulation, even over here, you will find this top bar which is very handy, and you can do most of the things to this bar. You don't need anything extra. So if I select create list, I can do that. I need to select over here just the thing have to be created. The thing can automatically it will close this setup. So huge effort, unlike many softwares where they need to put in a lot of effort to create all these components, where it is more CFD oriented and integrated into the SolidWorks CAD module and create those leads automatically over here. So this what we find out from a understanding perspective, we just scroll the model, find out any such gaps and fill them with lists. These could be places where either we are giving some kind of input session, that is air is coming inside or is going outside, or it could be just a case wherein you need to actually close this particular entities or I would say holes. If necessary, if it is a complex geometry and you are not able to understand where leads need to be created, then you can use this option of leakage tracking. If you find out the location where the leads have not yet been created. Simple geometry, however, if it is a complex one, then you might want to use this to understand how to create those particular leads or the location where they have to be created. I know how it works. If you can see here, it is asking for the start page. So for that, and and the expected exit space. I do that, and I can it to find how it is going to work. Now in this case, you can see I have just selected these two phases and press the calculate. It is showing the full way in which the fluid is going to flow. So I have not stalled. I have not even created a flow simulation setup. It is just showing you how it is going to flow from these phases that are selected. Can be a case when I don't have a lead over here, or there's some holes, etc. throughout the setup, and this option you can understand how the lies, uh, um, how it's going to leak out of the setup. Find out those locations and fill them with lead. I don't know how this came up. The trial license for each company or each register. I didn't understand this. What do you mean by register? This is a new word for me. But don't worry about the trial license. We're here to help you understand how the software works. This takes in terms of 15 days or 1 week or 30 days. We'll ensure that you are comfortable with the software and see, as you're doing it in hardly 90 minutes, you will complete field of the software. So in 15 days, I believe you should be an expert in the software. The only knowledge that you will be required is an understanding of your the analysis that you want to do. That's it. Let's the works the way we start off a flow simulation study. We are here flow simulation project wizard. Okay, this helps us create best things or the core that that is required for analyzing a certain thing. So give a name for this particular study. We can configuration to use. So I created a new configuration that can go here directly. That means active configuration, and we can say use current. The configuration name is test. It is already showing you it there. If see, we have an option to select unit. We can create a new set of custom units. However, the option there is a set of default unit combinations that are over here. So the initial words that I use, that is the internal or the external flow analysis, that decided over here. So internal is going to be the way what I'm doing here, wherein it is a closed entity. Even that within this internal closed domain, there could be small closed entities or closed loop in fluid is not flowing. So if such are there, then you can select this option and say exclude cavities without flow condition. So that will exclude those things. Things which you can see over here, we can select whether you want to simulate heat or temperature inside the system. So yes, you can select it. It could be a case wherein we don't want to simulate fluid, it is all static, and select that this option and make it all static and only will be solved. If radiation effects are necessary, then we can select it and also be taken into account. Could be dependent. If you remember one example which I showed initially, wherein we understand the behavior over a period of time, then we can use time dependent options. Obviously, software does not know how this particular setup is positioned, so that will help us give the direction of positioning of this component. We'll cover one example on this and we'll see how it is going to be. But if any rotating components like blowers, etc., and you want to simulate, then this option is going to help you do that. After, the next important thing will be deciding the fluid that will be used in this particular analysis. So use set of different fluids. I'm going for a liquid. I will select water over here. I just double click and the fluid will be added over here. If either the flow will be turbulent or linear, then you can select it, or leave it at laminar and turbulent. So based on the speed and the turbulence that is seen in the entire system, the change kind of equations that will be used for solving. Also have cavitation effect being simulated. Uh, Moving on, if basic things like we want to specify the conditions, thermal effects are present and these come into picture. Else can leave it at adiabatic. There is no temperature interaction happens between them. We specify the roughness of the walls and initial conditions like what will be the initial pressure, temperature, and if it is a global system or external flow analysis, we can also specify velocity directions or velocity values. Specify a few global turbulence parameters as well over here. There are these two kind of parameter inputs that we can view for it is mesh quality. This software can default help us create the mesh using these bars over here. So the purchase from 1 unit to 5 unit is more towards mesh refinement. So it will refine the mesh more and more based on these particular settings. The most advisable one, it is the default one, and it creates an optimal mesh. If necessary, you can refine it further. And from 6 to 8, I would say it is more towards your convergence of the different parameters. It is going to tighten the convergence parameters, and we should be able to see more accurate results here. We have a few more broader level controls for the mesh. Include manual specification of minimum gap size. So usually we can specify the smallest gap that is present in this particular setup. So the elements that will be created, or the software will search for that gap and ensure that enough elements are created within that gap. It could be thickness, there could be thin structures inside the setup, and we can do those things also, and those are captured properly. And say there are few other parameters which I will not discuss too much now, that is like advanced narrow channel refinement and optimize. And I would say these would be the basic or level input that we are giving to new in flow simulation. It is the first step that we have done. If you block a box like thing that is created, that is what we call as computational domain, and this is the place where the fluid is present at the moment. So the software has automatically detected the air the fluid is present, and you can visualize it. These are other things like application of boundary conditions. Now, say the office is entering this plus phase with these things. We can specify the mass flow, volume flow, or we can specify the pressure or all condition that we want to view. And decide whichever input that we have, those can be input over here. So if mass flow rate, if you can over here, it is like 0.000, that is the default value. I'll change it to say 0.7 kg per second, and based on the tutorial. So don't ask me where I get this value. It is more of the example, but need to know this value in detail. I would argue that this particular bar is very sensitive. If you want, it also works as a calculator. Any other input that is given can change automatically in the default unit. So instead of, say, in this particular example, I have 10 meters per second. Maybe I don't know the input in meters per second, but I give it in millimeters per second. I can do that. And on coming out of the box, the unit will be automatically converted to meters per second. So it's like a calculator. It's sensitive. I can do the changes for you. So this is in terms of input, you can also specify whether the input is non-phase, or if there's any swirl inside the input, or if there's any vectoral details that you want to view wherein the input is coming at different directions. Also say fully developed, Typically, fluid will be in a parabolic shape when it comes inside. Velocity is minimum at the ends and maximum in the center. So behavior can be captured immediately as soon as um, behavior can be the initial state itself when we are giving the boundary conditions. The parameters like temperature uh, can be specified. Turbulence details can be given. We give boundary layers also. And if necessary, over here itself, we can select this option of create associated goals, and it will be created on this particular setup to ensure that it is converged. Okay, so this is the first input where we are telling how much fluid or is inside, either in the form of mass flow rate or volume flow rate, or would be also a pressure condition. The outlet, maybe I know the details at the outlet and I can leave it at a pressure condition with an environmental pressure and let the software calculate the other details for us. So I'll do that. Here we have these different options. It could be a global goal wherein I want to converge on certain things, or that the convergence is the maximum level of velocity, maybe pressure and density. So what important things are there, we can select over here and just accept. So this is the global pressure, is goal at the point, surface, volume, or you can create your own goal using an equation over here. Good case wherein I want to write an equation of the different goals. I want to find out, you can say an example could be I want to ensure that the pressure drop from the into the outlet is as per a certain value and is converged. That can be done. So these would be basic conditions that are required to create a setup. I will just show you how it works and the different options again was here. So if you see, once I say solve, we have things like initially it will mesh it, like solve, new calculations are done. You can specify whether the computation has to be done on this computer or on a remote computer. So this simulation has option to do computing. We can also specify the number of CPUs to be used on this local computer. So at the moment I have got 8 over here, so it is showing 8 over here. It could batch analysis. If you multiple projects that I've created, you can trigger an overnight and the software is solved for you. So on transition, we'll get this particular window. You can see the different options. We can see convergence happening. At the moment it is meshing the setup, so those that are being finished. The meshing, we can option here and do further details, or we can verify the convergence rate is going. This is going on. I'll check the chat window. If there are any questions, feel free to use it now. I would like to cover. So first, I would like to show you the convergence graph here. You can see where it is going to show you the convergence. We can see the way the solution is happening over a period of time, so you can see the result as well being solved. Also see the kind of output you want to monitor. It could be anything, velocity, pressure, or temperature. So it looks this is a thing wherein it has solved and we are able to see it. Experiment, it is almost done the solution. It is kind of saving files and it is going to come out. I don't taking a break for a minute or two. Please use the chat window to ask any questions which you have. take the question. First, more towards when to be used at the outlet, whether it should be static pressure or environmental pressure. Now, interesting thing, there is a specific thing that has to be used. As I told you, we need to understand these facts before the analysis is done. If we don't know the outlet conditions and we are expecting the fluid to go into a atmospheric condition, or it's a huge pipe on which it is out, then long in keeping it at environmental pressure, and the software can calculate the static pressures for you, or the absolute values of pressure, then definitely use them the static option. And that is more advisable, no doubt on that side. Of the wall, can you configure it to automatically access if the wall is closed or open, or these need to done separate studies? Yes, the way it works is, number one, you drive it through these configurations. You can create multiple wall conditions where the wall has different angles. Also have this thing called as parametric study. You change or create a particular angle for this particular wall. Maybe it is we can create the rotation. We specify different angles for the wall, and we can solve multiple iterations on using that. Finally, I think called as automatic over here. That works is we are going to specify the details of the actual location of the wall, and the software can do the calculation for us. From the parametric option or parameter editor, wherein we can use some parameters on which it can iterate and solve it for us. There are no further questions. Is solved and has some results. And going results part of it. Results over here is unlike in simulation, it is not that we are seeing the results on the complete part. Typically, it will be at a certain cross section because we are interested in seeing the variations inside fluid. So that becomes completely different. So we have something called a cut plot. We can cut plot. The rest is for creating the cut can be a plane or since that you want to select. The software can create the cut. We can specify the value that has to be shown or will be shown over here. So it could contour here, and let me show it over here on the screen. In this place, at the moment, you are seeing pressure distribution at a cross section. It could be velocity, details like, okay, in this case, pressure and velocity are the only two important things. We also have the option of ISO lines over here. We can remove vectors and see them. It could be also the stream lines, which are very interesting. Now, when I zoom in, the lines are increasing, showing us a more detailed view of the movement. This is dynamic in the sense I can hold this and move manually to see the of the results across the thickness of the cross section. Option is also there by which you can see the variations on the 3 profile. One more way of visualization, you can see it is more nice to see this one, which will show you fluid is moving, especially these. If you can see, there is a bit of recirculation that is triggering over here at the end, so we can visualize that. So I think these are a few options that are present over here. You can explore it in more detail later on. Surfaces, so just the way we saw it for a cut plot, we can see the results on a certain surface, and typically this could be cases like at the inlet phase or the outlet phase, or to find out the forces coming on a certain phase, etc. Those can be again visualized using this option. This other things like isosurface, we can use an isosurface to see the results. Finally, other interesting one will be trajectory. So specify the inlet or the location from which you want to see, and the number of trajectories that you want to see. On that, the software can show us how the fluid is going to flow inside the system. You have those trajectories. So over here, I'm going to animate it at the moment and see the it goes. You can see that it is just flowing, the way it is flowing. You can see a few lines which are coming from the outlet. Nothing but the reverse flow that might be happening. The initial pressure conditions, the flow actually coming in even from the outlet, oscillates and goes back. Other could be, if you are interested, we can do particle study. We can insert certain number of particles at the inlet, and we see whether they go out of the system or they settle down in the system. And have surface parameters. We can do some measurement in terms of the quantity that is of interest. I told you it could be forces or torque, etc. So if I click that and show you, so I would be interested to show you in zero here, but it could be the pressure on that particular surface. It is of this value. So finer details can also be explored in a complete context, and there are XY plots giving the variation across a certain line that you want to see. We see how the goals are converged using this option. Finally, that to create a report, which is very important, and we have that option as well. So, if a basic analysis in flow simulation, this is the way we create and see the results. I believe this should cover or help you understand the way we do the analysis in flow simulation or fluids. Any questions? What are the next example? Okay, a few questions which I'm realizing now. Can we see them in a localized way or in detail? I'll show that local meshing, how to do it. Can I close look at which version of SolidWorks is this? Okay, the way I'm using 2014 version at the moment, which is released just a month back. And irrespective of the version that you're using, basic features remain the same. There will be more on add-on things which will come up, so you might find similar things. What if there is leak, and that is the case, we want to see what will happen to the wall. Okay, this interesting question. There is a question which says that what if there is a leak, and that is the case we want to actually see. Now, if we are simulating an internal flow analysis, we cannot in that particular scenario. If it is an external flow analysis, we can do it and permit certain leaks might be present in the wall, and we can visualize it. Can visualize the actual leak that is happening at a certain location. Or other way around, I would suggest to have a closed domain itself. The location, it could be a bushing or somewhere where you want to see if the forces are high enough by which it can dislocate the bushing and the flow can happen. Then we definitely use it and simulate the leakage through this particular bushing. Questions? Can I look at the mesh that is generated? Okay. I request you to use the chat window to ask questions because I cannot move through multiple windows. Now I'll just show you the meshing details a little bit more, as I can see a few people are asking. Into this one, something called as initial mesh over here. I'll call it example. Searching for calling this example. Okay, something called as initial mesh over here. Right click on the input and go to initial mesh. So one part was what we did here automatically. Part could be I don't want automatic settings. I unselect it, and then I can specify the details of the mesh. Now over here we have different options, like we can specify the elements across a certain length in the other direction or between a certain area. We can also have other details, like I can give a local mesh refinement over here. Let me show you the option. You can see the initial mesh. Using this, I can specify a certain surface or a volume at which I want to refine the mesh. So that we can create a junk geometry inside the system wherever I want to refine it, and select it and tell the software to refine the mesh at that location only to a very fine extent. In terms of visualization, if you want to see the mesh, it can be seen from multiple places. This one, right click on mesh over here and have a 3D view of the mesh. It could be cases wherein you want to see it in the plot. So if let me activate some no for a plot, and I can right click here. Results are not loaded. The results are, and I show it. I edit this. In the option over here, you can see here something called as mesh. I see the results. I see the mesh only, and then you can place the mesh at a certain cross section. So this is, you can see the mesh. Other way would be using this option. We can have 3D view of the different kind of cells that we have. It could be partial, complete, or details. So I move on to the next example. Any questions? Okay, this is using finite volume method, and there is only one solver. We don't have multiple solvers over here. It is the CFD solver for using the finite volume method. Any other you have? I don't see any movement in the question. Let me check the panel also. Okay, so it's a local mesh. I'll check if I get some time at the end of this session. I do it, or I would suggest you one of the examples online. It's not a big deal. It is a very easy option. You can do it. Okay. Now I'd like to move on to the next example. This is of an heat changer. Now, if I this particular setup, first of all, I'll go into the 3D geometry. Let me hide this. Okay. So this setup is the section of the setup. So it is here an external cylinder. There is an internal cylinder. There are a few inlets. Like some other cross sectional. Got it? Yeah. This is there is a inlet central cylinder, and there is one more axial direction. So axial direction, or the yellow color that you can see, this flows in that particular Z direction, and the outer cylinder, that is a blue cylinder, it has these two outlets through which it goes out of this system. So the geometry, the leads have been created here, and these have been created in product itself. If you want, you can create it in flow simulation the way I showed you before. If I go to the setup, If different things that will come into picture. Now here, as I told, it is a heat exchanger. One thing will be we are simulating heat. So I'm selecting this option of heat reduction in solid. So this layer is selected, so we are simulating heat. Second, fluid. We are selecting two fluids over here. It is not one but two. One is air, the second one is gas. So we are selecting two fluids. One thing is I just heating the gas, liquid or other. So my um, okay. Now once temperatures comes into picture, the other important part would be we need to also specify material that has been used for these solid components, the liquid component or case. Selecting those components over here, that is stainless steel. And one, if you remember previously, we selected adiabatic. Here we are specifying a heat transfer coefficient and give a value. This is how much heat is dissipated from the steam to the atmosphere. We are simulating the atmosphere here, but we are giving the convection coefficient and simulating that particular thing. Both are present and initial, no new thing over here. So I saw the extra things that were necessary in this setup where number selected the heat conduction option. In we have selected two fluids, we specified the material of the solid and we specified the amount of heat that is convected to the atmosphere. So these are the extra things that were necessary to be done in terms of basic input that we start off to create this setup. Second, now that we have multiple fluids, we created the details over here. There is something called as a default fluid. It is here. This has been selected as a default fluid and it is water or liquid. Now this fluid is assumed to be present in the entire system. However, there is one more closed domain inside this system which to be having air inside that. That can be defined using this fluid subdomain option. So what you can right click on it and select insert fluid subdomain. Select any phase inside a closed domain where air is going to be present, and that is it. It will automatically detect the entire rest of the setup and create the fluid domain. Hot air, which is working as the second domain over here. One is liquid, which is defined from the global setting. So this option that we are doing. If want global material which we selected, that is stainless steel, that will remain. If you want, if each of the metallic component has different material, then we can use this solid material option, insert solid materials, and we can specify material for different solid parts over here. The bottom conditions. Let's go on over here. The inlet condition. So here in water, inlet is there. We are specifying mass flow rate, which is at 0.01 kg per second, and we are giving turbulence as well. You can see here. For cold water, the fundamental pressure that is given at the outlet, from where the water will get heated because of the warm air that is moving inside and it go outside. The second is the hot air which is entering over here. This air is going to dissipate certain heat to the liquid, that is water, and when it goes out, it will go out at a certain temperature. We unify apart from the flow rate, we are specifying the initial temperature of cold water and initial temperature of the hot air. So if I outlet, calculate after the analysis is done. And over here, we are just specifying the average temperature of the tube, which central tube, which could help us guiding the entire analysis. So create the setup with always, and if I go into the results, the is something like that. Let's components transparent so that we can see that. This will look. This is the question inside the system. You can see it is the clear distinction between the temperature distributions that are happening over here. So this cell air is quite hot, which is ranging in the 200 Kelvin, and the blue one is the other of it. So information makes sense here. No, sorry, this is moving at cross section. This may not be of too much relevance. So other important or interesting part could be I want to see the way the fluid is going to flow. So selecting one particular inlet over here and we are animating it. You can see coming in over there. It moves empty cylinder, central cylinder. So this or design this particular heat exchanger wherein fluid can be visualized, or we can see how it is going to flow. We can have some kind of components which will help design inside the heat exchanger so that the fluid is to the maximum extent, it covers the maximum area and it gets heated to the maximum extent. Obviously, to define the efficiency of the heat exchanger, efficiency could be anything like radiators or boilers, etc., which can be simulated using this approach or module. Okay, in terms of my second example on heat exchanger, I believe these are the important things that I would like to cover. And any questions while I move on to the next example? One of the questions is, can the software calculate the overall heat per coefficient for this case? Say there is an automatic option, but the one that I showed you, the goal, use this, we can specify equation goal to any kind of output. We need to specify those details over here. You can see this is a very easy interactive calculator. We can directly take the inputs from the front end over there and we can calculate the heat transfer coefficient. It is that you have on the two examples that I've covered as of now. Okay, see any movement. So I assume there are no questions. Fine, example. This now. In this example, again, I'll first of all go to the basic settings. So not considering heat, so that is unselected. And then this example will be considering rotation. So that one is selected over here, rotation. And we need to specify axis which it is going to rotate. Now, if the entire system is assumed to be rotating, the simulation work is a bit different in the sense more kind of relative motion. If a fan is assumed to be rotating or is rotating in practicality, in simulation we are not rotating the fan, but we are rotating the air around it. That is going to create the effect of the fan. So what we are having, we do it in the software is we create an ET which is for rotation of the air around it. Modify the rotation of air around that particular solid component. That is using this option of rotation, and for all practical purposes we see very good accurate results here. We need to also specify the number of the direction of the rotation and the speed with which it is going to rotate. That's what here. Next, it is the same as before, nothing other differences. So The extra new option that we selected was the option of rotation, and we are using the global option. It also be a local option, and in that case we have to create a local cylinder and specify the rotational details for that particular cylinder. Now options could be inlet volume flow. So over here you can specify the amount of fluid that is coming inside this system in the inlet. That can be environmental pressure, and finally stator wall. Now this is an interesting concept again, just following the same points which I mentioned initially. Then we are assuming that all the components in this setup that you are seeing on the screen are rotating. But in fact, this casing, which is I think more visible when I go to SolidWorks, is going to rotate. And if that is the case, then I just define the particular casing, this casing, as a stator, and what remains is these internal components which are free to rotate are only ones which are going to rotate. So that's done using the stator wall option or the real wall option that is present here. We select all those surfaces which are not going to rotate and tell software that they are stator. The ones which are not specified as stator are assumed to be rotating and will be taken into effect using the global rotating region option. Now, typically, other goals will come into picture, specifying mass flow rate, the inlet, outlet, average static pressure. One of the important things which I mentioned while one of the questions before was torque. So here we have selected torque as one of the calculation outputs. It's going to tell you the torque that is going to come on because flow that is happening or forces that are coming on all these fan blades. Specify the torque over here. Basically, it is going to converge on the torque and give us accurate values. It is also finding out pressure drop from inlet to outlet, and finally efficiency, which is very important. In this case, it is finding out the not the efficiency because the fade direction or shape. So then how much fluid will be thrown out of the system, or basically what is the efficiency of this particular pump. So you can have an equation out here. It pressure drop into inlet volume flow colon all this. I think you all are aware of the equations for efficiency of a pump. Out cut plots, you can visualize the results across a certain cut plot in terms of values, pressures. It's a very velocity. So those can also see surface plots if at all interested. So on the fin blades or the impeller blades, we can, I think one input I would like to show you and is not created here is the flow trace. You can see the gate. I directly select the inlet volume surface, so I need not search for that surface. Then right click flow trajectory and select it. So automatically that surface is selected. You can select lines and arrows, you can select number of trajectories and calculate it. To happen, let me have lines with arrows. This is okay. Maybe a few more trajectories. Let's animation of this. So this is being created by the rotating region wherein the fluid is coming inside and thrown out by this section. Fine. On this topic, almost at the end of this session, and 15 minutes, I'll quickly cover two more examples. I'll just show you the things that are present here. But meanwhile, any questions? Could you please derive the energy that the spinning impeller creates? You have specified the RPM of the impeller, and the impeller requires a given amount of torque that is calculated by the software. I say yes. Again, you need to use the equation, and you can do it. You can use the chat window. Anything, I'm moving on to the next example. This is more towards electronic cooling system module. Over here, we are going to use, I would say, the distinctive or different things. This electronic enclosure, as you can see on the screen, in multiple heat pipes, heat sinks, and electronic components which are present. The fan, there is a heat pipe, as you can see over here. In terms of setup, or the different things that have done or done in this case are the internal places. The option has to be selected. We are trying the gravity because heat comes into picture. The flow can also happen because of density differences. Solid, I think other things remain the same. No big difference. It is all similar to the example that we used to create the heat exchanger. Assigning different materials is fine. We are assigning some environmental conditions. The option over here is something called as fans. Okay. Now there can also be cases wherein we are not actually modeling the fan, but know that the fan is present at a certain location. In such case, we can just select the surface at which the fan is present. So a lead is created here, and that surface is given as the fan. This could be external fan. Now, in this example, on the left feature tree over here, you can see we have something called as external inlet fan. The fan which is blowing air inside the system, have an external outlet fan wherein the fan is blowing outside the system, and could be an internal fan which sits inside the system and takes turbulence inside the system. So this different options. So here an external fan is created, but the important thing is when you have the electronic cooling system, we use set of different manufacturers from whom we have details of different fans. If this particular fan selected here is from PAPST, and they have a set of different fans. We have details of fan parameters and the curve which is relevant to select a fan. The curve is present here, and that we directly used in the software. So this not only this particular set of huge set of fans, but you see other things like heat sinks, and things like fans, heat sinks, and printed surface. Yeah, they are the ones in terms of materials which present in the system, and these guided up when you have the electronic cooling system. So we are not going to model the fan, we are going to model the PCB or the heat pipe or the heat sink. They remain as junk components, and we can specify the details of the components, and software will simulate it for us. Other than so here, we have simulated contact resistance. So when two components are connected, the heat flow is not 100%. There's a certain amount of heat loss is happening. That can be simulated using this contact resistance option. It could be clips which are going to create the heat in this system. In simulation, we use the two resistor component to represent the chips, and are used to create the heat inside the system. And so I have heat pipes which are used to efficiently dissipate heat out of the chips into the heat sinks. And printed circuit boards, and we have the options to specify of layers inside PCBs. Also have a few ready-made PCBs over here. We can specify the amount of connecting layers present in these particular so this is what is goal and anything. You can see we have created huge set of goals. It includes the monitoring the temperature on certain chips, which is very important for analysis. Things are more towards conversions in terms of mass flow rate and other details. The vision is similar to what you saw before, but if result could be surface loss. Let me check this. Telling the selected the temp which are comparatively at a higher temperature. Bottom it is basically the RAM, and at the top there are different chips, and each sink is being measured for temperature, so we can see that. Other thing could be I want to see maybe how the flow is happening. Select these two environmental conditions and let me create a flow. This can show you how the flow is happening. Okay, from those two inlets, and it is going out from the player the fan is kept. So I would prefer increasing this number of trajectories. Okay. And let's animation of this. So this show is coming inside from different locations. It can locate different components inside this particular enclosure. So this electronic cooling system module. While I move on to the next module. What I discussed is the model that I showed you, that is heating, ventilation, and air conditioning. The different capabilities, but interesting part or one cool thing is something called as tracer study over here. Now, by the way, this is an external flow analysis. So you see we have selected external. This is all time-dependent analysis. So that option is selected. There is single fluid is present, and other options are almost the same. Exit velocity, which is defined in the direction using the dependency option. An equation is being given for that is flowing in the Z direction. Typically happens if it is atmospheric condition or if it's a complete environmental condition. The velocity of the wind varies from top to bottom. That is at a certain height, the velocity will be different, and it goes on changing as we go down this system. So to simulate that scenario, we are giving an equation here, and that has been given as a global condition. So if at all it is a external analysis, then we can specify the inputs over here itself, and is now of a kind of grading around it, and we are simulating if a truck or a vehicle is going to create something for after the analysis, we can visualize how that pollutant is going to move out of the system. Kind of the pollutant and it goes in a certain way. So this is the example. Second, we can also visualize on this part of it. So in terms of parameters, instead of velocity, we get that particular parameter of matter and see the variation of matter nitrogen oxide inside the system that can help us understand how clean the streets will be, how if all it is a closed thing, we can ensure that the human beings who are present there are exposed to too much of nitrogen oxide and lead to some health problems. So frankly, that is what I wanted to cover today. Um, I have any questions that you have, or else I would like to go into the conclusion part of it. Please use the question. Just simulated the one that I showed you over here. One question is, can we simulate time effect, that is over a period of time what happens? Of course it can. The example shown on the screen is related to that. It is a transient analysis because we want to see the effect of nitrogen oxide over a period of time, or how much time it will take for a solution that is created at a certain location to defect out of the system. So time is relevant over here, and it has been simulated. Please ask if any questions that you have. So as the examples that I have covered today, we'll try to share this presentation with you. The rec is also available, and the examples, the actual models are present at the location that has been given here. You're into the flow simulation, install a directory, and a folder by name example. So finally, we'll to this particular session, I would say either one of our marks, or feel free to contact them for your evaluation license. I'll be getting a poll now, so that know who all are interested in evaluation license. Let me on the poll for you. Okay, this is open. Please vote on whether you need an evaluation, or a few other questions have been asked, which will help us understand how do you want to go ahead with it. Second, evaluation license for flow simulation. If you are interested in the other two modules, that is HVAC and ECS, please ensure that you ask for it and you get it. In the help. So these examples are all present in the installation directory. I show the location for you. The examples that I have covered are one each from the basic, inter and high-end analysis. Try maximum examples of your interest, or the ones that shown you in the first few days, at least 7 to 10 days, and thereon you are, I'm sure, will be confident enough to start example to be solved in this setup. And feel free to contact me or your VAR. I'll be in touch with you, ensure that you're not stuck anywhere, and get all the possible help to this particular to get a good understanding of the software. All fits your requirement and you like it, you are open to instance the software. I would encourage to do that if it fits the requirement. File is already open. Please give your opinion on if you would like to have an evaluation, or if you want to. I'm sure it is not that you all could be busy and you want to evaluate it sometime later. Of course, you can do later also. If you want, you can select the second option wherein you can tell whether like us someone just to have a discussion. It may be wherein you are not understood what I have explained here, or you want some more inputs on the software. Feel free to do that. I like to request a demonstration, so you can also have a personal demonstration of the software. You're all welcome. And finally, I use other software, so you can select any one of them and do that. And through the poll, I believe you should be able to see the poll window, which is already present on the screen. I started the poll. Okay. In the meanwhile, if you have any questions, this is the chat window. I am open for questions. Okay. So it is open for another 5 minutes. Please feel free to give your input on whether you need an evaluation option or whatever other options that you want to select. Secondly, please use this window. I'm open for questions.